Albert Einstein once remarked, "The significant problems we have cannot be solved at the same level of thinking with which we created them." This presentation provides an overview of problem solving, describes models and strategies, and offers applications for medical educators. As mentioned in previous sessions, learning is enhanced when taught in the context of use, and providing students with opportunities to work with authentic problems helps them make connections, generate meanings, and develop skills. Becoming an expert problem solver in a specific domain requires learning the content of the domain and problem-solving methods that experts in that domain use. It involves recognizing when additional information is needed, such as how, who, what, where, when, and why. Problem solving involves higher-order thinking skills such as visualization, association, abstraction, comprehension, manipulation, reasoning, analysis, synthesis, and generalization. Expert problem solvers manage and coordinate these skills to be able to arrive at solutions successfully and efficiently. They have a grasp of common problem-solving strategies used in their domain and are able to invent new strategies when needed. They can also take shortcuts by recognizing how new problems resemble previously solved ones. Problem solvers may tackle complex problems by breaking them down into smaller, intermediate goals as they work toward building a solution for the larger, final goal. Learning to be able to successfully solve problems in a specific domain involves gaining declarative and procedural knowledge, or the what and the how. While declarative knowledge items are the facts, concepts, and principles of the domain, procedural knowledge is the understanding of problem-solving strategies for the domain. Problem solvers organize declarative knowledge needed to solve problems in mental models, or schemata, as discussed in the presentation on meaningful learning and schema theory. These mental models make it possible for a student to represent a problem in their minds, access needed information, and work through possible solutions. Students apply procedural knowledge to this as they select and invent strategies for solving a problem. Expertise in problem solving is domain specific, meaning that an individual can be an expert problem solver in one field and a novice in another field. While some higher order thinking skills and problem solving strategies developed in one domain can be useful for solving problems in another domain, to become an expert in solving problems involves having extensive declarative knowledge in the domain. Experts can draw on past experiences solving similar problems as well, and this helps them to more efficiently identify necessary information needed to solve problems at hand. As mistakes during problem solving often involve misconceptions about key concepts in the domain, experts avoid such mistakes by having a solid foundation of relevant declarative knowledge. Expert problem solvers exhibit positive attitudes toward problem solving. They are motivated to attempt and persist at a problem until a solution is reached, and they are confident in their ability to solve problems. Becoming an expert problem solver also depends on the way the declarative knowledge is organized in the mind. Experts typically have accurate, complete, and amendable mental models of the declarative knowledge of their chosen field. Experts also recognize that some problems contain greater variability and can thus have more than one solution. As this The Far Side comic illustrates, there's more than one way to solve the problem of a runaway stagecoach. The first method involves 6 distinct steps that invoke risk to the problem solver. The second method is more effective and efficient, though the horses don't fare too well. Problems vary in the amount and way that they are structured. This structural variability is thought of as a continuum, from well-structured to moderately structured to ill-structured problems. Well-structured problems typically provide all of the needed information to the solver, and solutions converge to a single right answer. The strategy for solving the problem is usually quite clear and predictable. Moving along the continuum to moderately structured problems, we see that some information is provided to the solver, and the rest of the needed information can usually be gathered. Like well-structured problems, there is usually a single right answer, but there may be several acceptable ways to arrive at that answer. Ill-structured problems are thought of as having unclear or vague goals, and information needs to be gathered in order to solve. There may be several possible solutions or no yet acceptable solution. Often, several strategies are needed to solve ill-structured problems, and strategies may need to be adapted, combined, or invented in order to solve problems. The amount of declarative knowledge needed to solve problems also follows this continuum, with less structured problems requiring more extensive and deeper knowledge. Authentic problems are often complex and composed of several smaller problems that vary in structure. Expertise in a field, therefore, involves being able to solve well-structured problems, such as routine tasks, as well as moderately and ill-structured problems, and thus students in a selected field need to experience solving problems along the full continuum. Here are some tips for teaching problem solving. First, it is recommended that both declarative and procedural knowledge be taught together to help students build mental models that contain connections to both. Lead students to recognize their mental models and use them to make predictions or explain events. Help them also to recognize the strategies that they use and how these strategies can be improved to be more efficient and/or effective. Providing ample practice in solving common, well-structured problems will enable students to develop automaticity and improve their efficiency. Don't neglect providing students with opportunities to solve less structured problems as well. It often requires more time, but they will be able to transfer their knowledge, strategies, and experience with solutions more readily to new problems. Problem solving is best taught in the context it will be used, so lead students to make connections between their learning and authentic problems in the domain. Teach students how to appropriately break complex problems into manageable smaller problems with more clearly defined goals. As instructors, we can help students learn from their mistakes and limit many future mistakes by identifying and correcting misconceptions. Provide a supportive learning environment in which learners are encouraged and motivated to tackle and persist in solving problems in the domain. As problem-solving expertise is domain-specific, there are specific models in the medical domain for solving problems. The hypothetico-deductive model is a sequential, step-by-step process that involves acquiring data by search and scan, followed by interpretation of data, further hypothesis generation, and evaluation. The illness scripts model of clinical reasoning describes the knowledge structures of experienced physicians as illness scripts. These scripts are developed through the professional's experiences with patients and contain little pathophysiological knowledge, but are rich in relevant information about disease, its consequences, and the context in which it develops. There are 4 script development stages in this model. 1. Development of elaborated causal networks. 2. Compilation of relations between elaborated networks and abridged ones. 3. Emergence of illness scripts. And 4. Storing of patient encounters as instant scripts. Having a sufficient repertoire of scripts allows the expert problem solver to understand problems more fully and explain findings with relevant declarative knowledge of the medical domain. The probabilistic model defines relationships between clinical variables in statistical terms, such as frequency or prevalence. Hypotheses are generated and then weighed on the likelihood that they could be true. Hardin, 2002, describes 2 strategies commonly used in the medical domain for solving problems. The first is forward reasoning versus backward reasoning. Forward reasoning is the development and proving and disproving of hypotheses based on available data. Backward reasoning begins with the predicted outcomes of a hypothesis and moves to finding and analyzing data that would support or reject it. The second strategy is top-down, also called broad-narrow. This means that problem solvers begin with broader concepts related to a problem and then work toward narrowing their focus and possible solutions by collecting relevant data. The choice of strategy for diagnostic problem solving depends on the perceived difficulty of the case and on knowledge of content as well as strategy. Final conclusions should depend both on prior belief and strength of the evidence. Because of cognitive limitations, systematic biases and errors result from employing simpler rather than more complex cognitive strategies. Problem solving is incorporated into medical education in several ways. One popular application in this context is problem-based learning, or PBL. PBL involves presenting small groups of students a real or realistic problem to solve, and resources, guidance, and structured approaches to solving it. Trigger statements and visuals, such as images and video clips of patients, are used to communicate patient characteristics, clinical presentation, and other background case information. Students are actively involved in PBL, and they have to use communication and critical thinking skills to work through the case with their group members. PBL is an effective approach to developing diagnostic competence in students. It also supports the growth of self-direction and critical analytical skills. PBL can be used in small and large group formats. PBL develops group learning practices, assists students in understanding and learning curriculum content, and supports students in gaining skills for problem solving and reasoning that they will be able to apply in their professional lives, as stated by Sefton and Frommer 2013 in their chapter on PBL. Some topics work very well for using the PBL approach and others may not. There are many resources that provide pre-written cases that can be used in PBL, though you often would want to modify the case materials to suit your instructional situation. If you plan to write your own PBL cases, Azer and colleagues 2012 advise you to write the problems in a team with colleagues from disciplines that would be represented in the problems, such as basic sciences, clinical medicine, radiology, professionalism, psychological medicine, etc. Define the educational objectives from the beginning of the case writing process and refer back to these objectives at other points in the case development. Azer notes that a good PBL case should demonstrate logical flow and allow students to use knowledge obtained from history, examination, and investigations to revisit their hypotheses and rank them. The case structure should guide students to use evidence to justify their views and apply scientific approaches in the decision-making process. Another application of problem-solving instruction and practice is in the development and use of simulations. Simulations provide students with opportunities to solve simple, to moderate, to complex problems in structured, well-supervised, and safe environments. Some ways simulations may be used, as mentioned by Bearden and Page 2007, are to train students in how to break bad news, in how to respond to clinical situations where the potential of sexual impropriety arises, in general clinical skill building using standardized patients, and even in giving students a condensed but realistic sense of the experience of the changing needs and orientations of individual patients as they age in a doctor's client population. To review, this video has introduced characteristics of expert problem solvers and how to guide students to develop problem-solving expertise through observing problem-solving modeling done by experts in the domain, acquiring relevant declarative and procedural knowledge, and engaging in authentic practice and use of general and domain-specific problem-solving strategies. Experience in solving problems, well-structured to ill-structured, in the field of study will enable students to later draw from these experiences to solve similar problems, and this will help them to improve their efficiency and accuracy in reaching acceptable solutions. Problem solving involves deep thinking and application and integration of ideas, concepts, and skills. It is necessary to achieving expertise in a field, and worthwhile for us as educators to continue to explore how we can better incorporate it into our teaching practices.